Sorry, guys. All right, was that good? All right, thank you. Sorry about that. All right, where were we? VXLAN. So it uses the same sort of topology, a leaf spine topology, but now traffic comes in through a leaf. It's encapsulated in a VXLAN header and effectively just routed across the network. So those spine switches are effectively just layer 3 routers now. There's no special hardware dependency required. And if we needed to, we can extend out to another data center, just routing that VXLAN traffic over a standard layer 3 wide area network. The other key thing we've done at this stage is to move the layer 3 boundary down to the leaf. Because we're now having to route at that level and encapsulate traffic there, we can also route customer traffic at that level. So within a VRF, we can go between interfaces on the leaf switch itself. Now, there's still some impact. This particular model here, we reliant on the routing underlay to provide all the connectivity. There's no native control plane within VXLAN in this topology. We reliant on routing protocol to find all the various leaves in the network, and we're relying on multicast routing to allow us to encapsulate broadcast or unknown unicast or multicast frames at layer 2, wrap them into a layer 3 header, and then route it across the network. And that can cause problems where we have now where we used to have a lot of layer 2 broadcasts, we've now got a lot of layer 3 broadcast traffic. And if we have that extended to multiple fabrics, then obviously that broadcast traffic is now going to multiple fabrics as well. We don't want that. So ideally, we want a way of being able to constrain how we learn MAC addresses in a more efficient manner. And that's really where we come to, where the modern VXLAN fabrics are today, which is we use a dedicated control plane for VXLAN, BGP EVPN. Now, this is really just a new address family into an existing multi-protocol BGP. And we still use standard BGP concepts. So the leaves become clients. The spines are, for the most part, at least some of the spines, route reflectors. If a leaf learns MAC address, it notifies the route reflector through BGP, and then BGP replicates that to all the clients for that particular address family. The only issue with this is that preemptive MAC address learning, like we have here, doesn't scale well. So if you have 100 VLANs with 100 MAC addresses and you want to be able to distribute that across your top-of-rack switches, then that's like 10,000 entries per top-of-rack switch. For MAC addresses that, to be honest, you probably don't ever need to use. So even though this is sort of the modern data center fabric, ACI takes us one step further, and we actually don't use EVPN internally within the fabric. We have a different control plane, as it were. And we'll go into that in a bit more detail later on. But I wanted to bring this up to kind of show where other fabrics outside of ACI, and if you built it yourself using NXOS, this is what you would probably build. Now, migrating to this sort of network has an impact on your operations. You now have a lot more switches, and those switches are more complex. We no longer have sort of basic layer 2 top-of-rack switches. They're layer 3, and they're running BGP. It becomes more of like a service provider network, really. So there's that impact, and we want to be able to then find a way to improve that and operate those networks better. Now, this is taken from a study in 2016, so it's probably improved a bit since then. But what we're saying here is that operating models at the moment aren't really working. 95% of all changes are performed manually. 70% of policy violations are due to human error, so someone's made a mistake, whether that's accidental or interpretation. And we spend most of our time, most of our OPEX, reactively troubleshooting and fixing the network. And that can be up to $60 billion US. So there's a lot of room there to improve how we operate a network. And that's an important part to how we built ACI. That's one of the things we want to improve. So one of the things we, out of the same study, was the fact that 22% of all network outages were caused by human error. Now, personally, I find that figure a bit low. I don't know about you. Quick question, does anybody know what this is? It's a VXR, well done, yes. I'll give you have a lolly, wherever that was. You all right? Yeah, go for that. Oh, yep. Yeah, so this was the core router of a small service provider I used to work for about 20 years ago. So our next question, does anyone know what happens when you run this command on it during the middle of the day? Well, yeah. So the correct answer is, well, really, it's an embarrassingly long drive to the data center to turn it on and off again. So when it comes to operating data center networks, we're primarily reactive. You know, we're troubleshooting as reactive. In some cases, it can make problems a lot worse than before. When we operate networks, we're still manually configuring devices, one device after another. And that obviously leaves room for human error, inconsistent configuration, and yeah, obviously that can be problematic. You know, you're not meeting the intent of the network. You know, firewalls are legendary for this. You know, people add firewall rules, but they never go back and clean them up. So over time, your firewalls become less and less of a firewall, and more of a router. So one way we can attempt to improve the situation is through automation, where instead of manually configuring devices, we use some form of fabric controller to configure the whole network as a consistent single entity. Now, traditional automation and software-defined networking, which I'm kind of using here as a terminology for automating the network, tends to deal with traditional networking constructs, so VRFs, interfaces, VLANs, and tends to be more focused at day two tasks, you know, obviously the ones you do more often. Add a VLAN, add a route, that sort of thing. There's still a gap, however, between the business requirement for the network and what gets implemented on the network. That requires the network administrators to interpret the requirement and configure the right thing. And the gap can sometimes leave room for misinterpretation and can leave room to misconfigure the network. Now, when we say misconfigure, it means we're using the automation tools as they were designed. We're pushing configuration to all the switches in a consistent manner, but it may just be the wrong configuration. We may be actually breaking something. Ideally, we need a network that's more intent-driven, that takes the input from the business requirements that are more close to the source and leaves less room for us to misinterpret. So this is where we come to intent-based networking. Now, intent-based networking is a relatively new term. It's not necessarily ours alone. I mean, certainly this is I think the definition actually is with Gartner for intent-based networking. And really has these three key pillars, translation, activation, and assurance. It starts with the translation layer, where we take the business intent as close to the definition that the business can provide it, translate it to a set of policies, pass that to more of an automation orchestration level, which is the activation tier, to actually implement those switches, implement on the switches, or the hardware, or the virtual infrastructure, whatever's required. And importantly, there's an assurance layer. Now, the assurance layer is here to validate that what has actually been configured is supposed to have been configured. It matches the intent as defined by the business, and that any future changes don't break things that have already been configured. And it's that feedback loop is the important part here. So in a data center, what actually is in the intent? Well, data centers are there to host applications. An application has an intent behind it. Application developers don't care about VLANs. They don't care about IP addresses. They don't care what host the application's running on. They don't care where the container is. Frankly, most of them don't care what data center the application's running in. They care about who the users are, how they access the application, and what other services are required to obviously get that service or application to work correctly. Now, automation, even intent-based data center automation, really comes into two categories. There, you can either do it yourself, or you can buy a pre-built platform. Now, what we strongly encourage people to do is to consider this and do what works best for your organization. Now, we're not trying to push anything particular on you. We want you to understand the need for automation and where it makes sense for you. Now, if you want to build your own, we're more than happy to help you with that. All our NXOS switches have an open RESTful API. Even DCNM now has a very comprehensive API for automation purposes. We support very common functions, netconf, and we have vendor-agnostic Yang models as well, OpenConf. And we have a large ecosystem of both open source and third-party automation tools and providers. People like Puppet, Chef, Ansible as common ones, vRealize suite as well. And if you really want to as well, we can run containers now on the Nexus switches, and on those containers you can run your own tools. So you don't have to run any of those either. You can make your own tools from scratch and run them at the edge. But doing it yourself takes time. It's time to set it up, time to operate it, time to manage it. There's a lot of, obviously, investment in intellectual property involved in setting that up. And that can be a problem, but for some organizations that's perfectly fine. They have the resources to do that. So the second option is an off-the-shelf pre-built platform. Now obviously if you buy something from a single vendor, like Cisco, you're going to get better support out of it because it's one place, one-stop shop. And it will hopefully have all the components of intent-based networking. So you have a translation, activation, assurance. We have all those components available for you. We have intent-based policy management. So we have pre-built best practice policies, including logical topology models that sometimes might be seen as being less flexible than doing it yourself. But that is a trade-off. What you do get is a network that's faster to deploy. It's a common topology, common configuration. It allows us to deploy that in your organization faster, train your people faster, and get value out of that investment faster. We also get integration to third-party applications such as hypervisors, firewalls. A lot of those integration points are maybe built for one customer and then be able to be shared across multiple customers. And of course, there's ongoing R&D as well. Obviously, Cisco, for example, is obviously spending a lot of money into ACI, improving ACI for all existing customers. So this at a high level is really what ACI is all about. It's a pre-built, best practice-based platform for DC networking automation. So hopefully now you've got an idea of the history of perhaps the data center networking, what ACI is at a very, very high level, and more particularly why we need ACI. So let's drill down into ACI in a bit more detail. Excuse me. So where does ACI fit in an intent-based data center? Well, ACI is that translation and activation layer. It's taking the intent, and we will show how we do that shortly, converting that to policies and automatically provisioning that across the network. The next component, and the next two components, really deal with assurance layer. Tetration is our reactive assurance layer. And now it captures flows of captures metadata about every flow across the network. And it uses both software sensors and hardware sensors to do that. And it uses that to build up an application dependency map, effectively learning how an application works. From that, we can, in some cases, can also be used for workload security. We can take that application dependency map and actually turn it into a set of firewall rules. The next part is a network assurance engine, which we really released about this time last year. And this is a whole different approach to assurance. It's proactive, it's modeling based, and it takes your configuration and how your network is currently configured and works out what is possible to happen on your network through mathematical models. Now, effectively, APIC is telling the network how it should be configured. Tetration shows what happened, what did the network do. And network assurance engine is more showing what could happen, what can happen on the fabric. So the ACI fabric itself, let's go through the components. It all starts with the APIC controller. So that's the Application Policy Infrastructure Controller. And that's our single point of management for the fabric. It does the automatic discovery and provisioning of all the devices in that fabric. It literally finds the switches by what's physically connected to the APIC controller. So it finds what's physically connected to its uplinks. From there we find the spines. And from the spines, we find the rest of the switches in the network. Now, we don't want a single point of failure, so we add additional APIC controllers. Now, these extra APIC controllers are either appliances or can be virtual machines now. We'll show you that a bit later on as well. But we have a cluster there. It's there, so we have no single point of failure. And there's no master, per se, in the cluster. You can use any of those interfaces, any of those boxes to configure the whole fabric. What we do is shard the database across multiple devices so that the information is kept in different locations, but there's no single true master server. Now, at this stage, we would add servers to the fabric, ideally through a virtual port channel. This gives us flexibility so that if we want to remove a switch or upgrade a switch, we can do that without losing connectivity to those end devices. We then add layer 4 to layer 7 services, firewalls, load balancers, intrusion protection. We would add those to the fabric again through virtual port channels, ideally, and these can be anywhere in the fabric. There's no requirement they have to be in a certain location, certain leaves. Any traffic that needs to go through those devices will be routed across the fabric to them and back and then on to their own destination. We then add physical routers. We typically do this through VRF Lite, so separate sub-interface per VRF, effectively, and then use OSPF or static routing or BGP, just like normal, to get out to the wide area network. The final component is, and we'll come to this in the ACI Anywhere section, the ability to stretch that fabric out to beyond just the data center to other sites, whether it's small sites, other data centers, or even up to the public cloud. So let's move on to the hardware we actually use in Nexus, in Cisco ACI fabrics. Well, there's two families of Nexus 9000 switches you might be aware of. The Nexus 9500 modular, the Nexus 9300 fixed form factor. Now, in ACI, we rarely use the 9500s. The 9500s we'd use for modular spines, and only for spines. We don't use these for leaf switches. And even then, we only use certain line cards of the 9500 to do that function. The reason for this is a little bit back to difference ACI and EVPN. We have a different control plane for discovering hosts and MAC addresses, and that requires some additional hardware and functionality built into the spine layer. So we'll come to that shortly. So we really only use 9500s when we have a requirement for a lot of switches. And we're talking like more than 64, that sort of range of leaf switches before we'd ever consider a modular spine. Most of the time we use Nexus 9300 switches. I'm showing here the 1 gig to 25 gig switches that we typically use for leafs. There's 3 families of chipset within the 9300 family. EX, FX, and shortly GX. I'll show GX in the next slide. So for the access switches, we typically use the EX or FX. The difference between EX and FX is very small, but there are some additional features in the FX series. Unified ports, so we can do fiber channel on the FX series, and MaxX security is probably the only other common one. But we still sell both EX and FX. They're both functionally fine unless you need those features. And the FX2, which is new, is really just port density, trying to increase the number of access ports in a particular top of rack switch. So, yes, sorry, yeah. 16 or 32, yeah. Okay, yeah, I can talk about that. There's some issues with 8 gig we should probably talk about, so, but yeah. 9300s, so in the 40 gig and 100 gig section, we really have 2 models there at the moment. We have, again, 40 gig access, and a separate set we're used for 40 or 100 gig spine connectivity. The 64-port one we've used for a couple of years now, and we've recently introduced a 32-port 1RU version of the same thing. Yes, sorry. Well, it allows you to leaf the spine and leaf to other spines, and you can actually extend that out as well from the spine layer up across the DCI network. So one case we have is where we've not encrypting everything, your leaf and spine traffic internally, but also the DCI network through a multipod. Yep. So we have just introduced, or announced at the very least, the GX series of 400 gigabit per second switches, if you need that. And these use a QSFP double density transceiver. So it's they look the same as the ordinary QSFP, but will now do up to 400 gig. So what would a typical, or perhaps reasonable size ACI topology look like? Well, it might look a bit like this, with 6 modular spines, 16 ports of 600 or 400 gig line cards, 200 access leaf switches, each with 400 gig uplinks, 400 terabits of access speed. Anybody want one of those? Anybody need one of those? Anybody need a single 400 gig interface this year? No? I'm surprised. So maybe that's, that's pipe dream. That's just kind of showing what we could scale up to theoretically, right? Realistically, we want to start down here. So we've spent a lot of time also making the fabric smaller and starting at a smaller scale. So we now have a 5RU ACI mini deployment. And this is, the only thing really mini about this is it's simply the minimum number of devices that you need to create an ACI fabric. There's no lack of features. It's still the same features you get in ACI. It's just a bare minimum. And we introduced virtual APICs into this so that we can start with one single physical controller and 2 virtual controllers to get the cluster that we need. So what about DC cabling? Well, DC cabling typically might look a bit like this. 7K, 5K, 2K, 7K in the core, 5K top of rack, 5K into road, 2K top of rack. Well, when we moved to a leaf spine architecture, that got complicated. So now, as of ACI 4.1, we have a multi-tier capability with an ACI. And we can do effectively leaf spine, leaf, leaf, the right way around. Other multi-tier topologies are coming soon. Now that allows us to reuse the same cabling, the same layout, and save you the trouble having to recable your data center. But more than that, we can move from 10 gig multi-mode SFPs to now 40 and 100 gig transceivers that still use the same single pair of LC-connected multi-mode fiber. So that's a 10-fold increase in your bandwidth without having to change any existing fiber as well. Now we'll move on to the network underlay. Now as the network underlay is kind of obviously there, it's there to provide that routing that the VXLAN overlay will route over. This is all automatically configured through APIC, so you never actually get to see any of this. You never need to worry about it. But under the hood, it's addressing links automatically out of a pool of addresses. We can create VPC pairs without needing to peer links between them by routing that traffic across the spine and back. And the important part is really the loopbacks. Again, these loopbacks are automatically configured. You get loopback for VTEP or virtual tunnel endpoint, VXLAN tunnel endpoint. You get a secondary IP at very least for multi-protocol BGP, just like a normal BGP network would. We had some extra loopbacks for places where you probably won't expect. So we have, on the VPCs, for instance, they get their own Anycast address. So each box gets a single IP that it shares, and that's used to route traffic and load balance incoming traffic across those 2 members through ECMP. The spines also have VTEP addresses. Now this is something we wouldn't see in a normal BGP EVPN network, and we'll come to that in the next slide as to why we have that. But once we have these loopbacks in place, we're using ISIS to advertise those across the underlay, and at least internally to the fabric, and also using PIM bidirectional as well to do the multicast routing. And we use, once we have those loopbacks in place, we set up multi-protocol BGP and still have route reflectors, typically on the spine layer, serving IP addressing to those switches. So the more important part is the overlay itself. Now, when we say integrated overlay, what we mean is that it's all automatic for you. You don't even really know there's an overlay there. You don't have to configure anything separate. But it is passing traffic. All customer traffic is run over the VXLAN overlay. Now, we use a particular version of VXLAN and ACI, generic protocol extension, GPE. Now, this is just like a typical VXLAN header, but it also includes some additional metadata fields that we can use for policy-based routing or flow-level control outside of just the IP addressing. So it gives us more flexibility to do more interesting things in the fabric. We still use traditional VXLAN virtual network identifiers, L2 and L3. And as I said before, we're carrying all traffic in that overlay, but that also includes routed layer 3 multicast. It's something that some of our other competitors are not able to do currently. Now, as I said before, we don't run BGP EVPN internally in the fabric. We have a separate mapping database that both learns and discovers MAC addresses and a mechanism of discovering that on other switches in the network. And we call that Council of Oracles. You may have heard it. Where the spines are all oracles, and they have a database, effectively every host in the network, every location in the network, and they have this Anycast IP address for the spines that leaves can use to basically go and ask, I don't know where this is, go ask the spine will deal with it. So instead of having to do an ARP to find where another location, another device is, and broadcasting across the network, we can instead say, look, I don't know where it is at the leaf, but I assume the spine's going to know. So I'm going to send that traffic to the spine. The spine's going to forward it onto the other leaf if it knows where it is, but it doesn't change any of its source or destination addressing. So when that gets to the destination address, it's going to learn that the source MAC came from the original leaf, and any reply traffic back to that will go directly back to that source leaf and learn the destination MAC. So you get this ability to learn the MACs on the leaves that you only need at that moment in time, but also not having to send traffic into any unnecessary hops. You're still sending it through the spine. There's no additional latency required. So we're far more efficient about how we manage MAC addresses on the top of rack switches. Fabric Anycast addresses are available within layer 3 interfaces. So on a VNI or network, we can establish an SVI on a top of rack switch that uses the same MAC address on every top of rack switch, so that when you route to that top of rack switch, it doesn't really matter anymore which one you're using. You're always going to find the same IP, you're going to find the same gateway MAC address, and then you're going to use the local VRF route table within that top of rack switch. Means we don't need HSRP between two devices, we don't even need peer gateway between the two VPC pairs. It's all very straightforward and works very well for that first hop from a server. Now I'd like to move on to how we abstract and talk about applications in ACI. Very much like the way a SIM card extracts the identity and configuration of a phone, and for those who use UCS Compute, the UCS service profile can extract the identity and configuration of a server away from the hardware. We try and take the same approach into ACI and extract the identity and configuration for an application away from the actual infrastructure itself. Now with ACI we have, well, it's all policy driven for a start. The way we do policies is really in two layers. There's what we call fabric access policies, then we have tenant policies, and I'll come to that shortly. Fabric access policies are really set up by the fabric owner, administrator, and that determines how we can use the fabric. In this case, we have really three common objects. There's policies, policy groups, and profiles. Now, policy is, as it may show here, is really talking about an individual functional feature. Such as LLDP, how we configure that, how we use port channels. We then group those policies into a collection called interface policy group, and they're set for a particular type of interface in this example here, say virtual port channels. We then use a profile to associate that particular group of configuration, or that policy configuration, to an explicitly set of interfaces themselves, and that's done through that profile. Now, this interface group profile hasn't actually been applied to anything yet, because the interface group profile has to be applied to a switch in order to actually be implemented. So in our switch policy, we have the same sort of concept. We have switch level policies, a switch level policy group, and then we take that policy group, combine it with a set of switches, and then as well as the selected interface profiles. And this is where we start actually implementing configuration. So we now have a configuration for a set of leafs, the set of interfaces, and what we get is on the right here. So we've now configured these two leaf switches, we've told them that's a VPC, we've set up a VPC interface, and that's effectively the implemented configuration. Now, why we do it this way is really all about reusability. If we want to change the way we configure something like NetFlow, we can configure that across the whole switch, or all switches at once, if they all use the same policy. If we want to extend configuration, we can add a new switch to a switch profile, or we could add more ports to a port channel just by adding them to the selector on the interface group policy profile. Excuse me. The other key benefit here is if a switch dies, all the configuration is held within those policies, and we can replace a switch, put a new one in, tell it it's the same role as the last one, and it's going to inherit those policies and all the configuration that goes on with it. Now, the second half of policies in the fabric is the tenant policy. Now, what we've done so far is talked about interfaces and how we use the fabric and how we set up those switches, but we haven't talked about VRFs or IP addresses or VLAN IDs. These are all done within the tenant policy. Now, the tenant policy a tenant in ACI is really just a logical container for associated network and security policies. A tenant could be different customers if you're a managed service provider, or it could be different zones if you break up your network that way. So production, development, maybe DMZ could be a tenant. Each tenant has its own isolated resources and can have separate administrators and separate AAA domains as well. Within a tenant, we have one or more VRFs. Now these are normal VRFs, just like you would use today. They are mapped to a particular layer 3 VNI, or virtual network identifier, in the VXLAN fabric. So each VRF has its own ID. Again, VRFs are really just used for IP address separation, segmentation. Within a VRF, we have a concept of a bridge domain. Now, a bridge domain is really a layer 2 network, or layer 2 zone. It's at layer 2 or multicast broadcast scope. And that's mapped to a layer 2 VXLAN VNI identifier. And we can, if you want to think of it as a stretched VLAN across multiple switches, that's a good way of thinking about it. And like a VLAN, we can also put a layer 3 SVI on that. And that becomes that top of rack anycast address that we talked about previously. Now, importantly, the next, and this is really where we start differentiating ourselves between an ordinary BGP EVPN network and ACI, is we have the concept of EPGs, or endpoint groups. Now, I'll go into this in more detail shortly, but an endpoint group is really a collection of servers. And they themselves belong to a bridge domain and to a VRF. And really, they're almost like a sub-bridge domain. And they get their own layer 2 VNI, and they can have an optional layer 3 SVI as well, as shown in this case. Now, what we're showing here is a static EPG, and we can show this more detail in the next slide, but effectively this is where we map a interface and a VLAN ID into that particular endpoint group. So any MAC addresses and IP addresses associated to those will be learned as part of that endpoint group through those interfaces. Now the next part is layer 3 outs. Now these are, as the name kind of implies, how we get out of a VRF to an upstream layer 3 network. And these are effectively routed interfaces. Now that's access sub-interfaces or even routed SVI interfaces. And this is where we do policies for dynamic routing or even static routing, OSPF, EIGRP, BGP. And we do traditional things like route maps, prefix lists to do manipulations. And so this allows us to learn networks outside of the fabric and be able to send traffic both in and out. And we use these L3 outs to define the final type of EPG, or an external EPG, which is effectively a group of objects outside of the fabric that we want to talk to. So what is an endpoint group? Well, basically it's a collection of servers that provide or consume a common service. Now examples would be in a 3-tier model, web, app, database. Those are 3 separate endpoint groups. If it's a DNS, it's really just one single endpoint group. It's a much more simpler application. There are 3 ways that we, so first of all, EPGs are fundamental to the ACI security model. The way that ACI security works is that we need to identify these source and destination object groups in order to apply things like ACLs, do service chaining, route leaking, or even routing inside or outside the fabric. There are 3 ways to do that. We have static EPGs, as we mentioned in the previous slide, which are the most simple option, simply mapping an interface and a VLAN ID to an endpoint group. And I should say that VLAN ID and that switch port, they're totally unique. They don't have to be the same VLAN ID on each interface. It doesn't have to be the same VLAN ID on every switch. It's totally up to you how you map that. So there's more flexibility there. The second option is a dynamic EPG, and this requires the use of a virtual machine manager, such as vCenter, which is a common one, but also a system center for Hyper-V, and now containers as well. Kubernetes is a good example for that. And what we do with dynamic EPGs is that when we create an endpoint group in the fabric, instead of assigning it a static interface and the VLAN ID, we basically tell the virtual machine manager to create a virtual port group, for example for VMware, a distributed virtual port group for that EPG, and we will dynamically tell it what VLAN it should be using when it trunks that out of the network, up to the leaf switches. So you don't have to worry about allocating or configuring those virtual switches. It's all done for you automatically. And you don't have to worry about allocating VLAN IDs for that. That's all done automatically. And this is all just using standard APIs. We're not talking about, there's no kernel module VIBs or anything required. It's just simple APIs into the vCenter. The next point, the third option here is micro-segmentation. This is obviously becoming a bit more of a security-led requirement. And this allows us to group servers at a sub-VLAN level or sub-IP network level using a combination of attributes. And these attributes could be direct ones, such as the IP address or the MAC address of the host, but are more likely to be some sort of custom metadata. So we could use perhaps the DNS name for that host, do a reverse lookup, what AD group it belongs to, or more likely in the virtual machine world, if it's got any custom attributes or tags or what folder it lives in. And we can use that to build a definition of what an EPG should be. The final type of EPGs, as I mentioned before, is external EPGs. And these are really just basic network objects. For anything outside of Fabric, the only way we can identify them is by their IP address. So these are really just basic network ACLs that we still need to use to do the inherent security in ACI. And we'll talk about that shortly. So if I can now go back to what an application profile is. Now, as we mentioned before, we're trying to abstract the identity and configuration of an application away from the infrastructure of the fabric itself. So under a tenant policy model, we have the ability to configure these application profiles as a collection of information and configuration about a particular application. Now, if you were to draw a typical three-tier application, if such a thing actually exists anymore, you might have web servers, application servers, database servers. They might be in different subnets, and you'd have a router or a layer 3 firewall between them. You would have ACLs at certain points in that path, whether it's coming in from the wide area network or between your app and DB, wherever it is. You might have intrusion protection. You might have a load balancer, an application delivery controller, web application firewall. You might have extra services in there. And you might want to actually span copy traffic, payload traffic out at certain points of that application as well. Well, this is the abstracted view that we want to take into ACI. We want to take that model and literally implement it as close to that as we can. So the first thing we do is assign EPGs. So as stated, we have EPGs for all those groups. Those EPGs would also own those particular subnets and IP addresses. We define, at the very least, an external EPG, identifying who our end users are. And now, probably the more important part is we define contracts between those EPGs. Now, a contract is, as the name implies, is there to say what explicitly is allowed between one EPG and another. Now, a contract can contain a filter. A filter is basically a layer 4 basic firewall, and it can contain other things like QoS or, in some circumstances, service graphs, which is our way of doing policy-based redirection, and how we break out to other services in the fabric. We also do copying functions through a service graph as well, payload spanning. So what are the benefits to this approach? Well, now we've abstracted the configuration of the application away from the infrastructure. It allows us to move that configuration around. So we are now location agnostic. We can move from one data center to another without having to make any configuration changes. We can extend or split these configurations between data centers. So you can have half your EPGs in DC1, half your EPGs in the DC2. You can, or half your members of an EPG, should I say. But you can also split the components out. So if, for example, you can move the web tier out maybe to a cloud provider, while still maintaining the app and database tiers within your own fabric. So we have a lot more flexibility with this. One of the common problems, though, and it's most people come to this realization that they don't understand their applications well enough. Most application developers probably don't understand their applications well enough, to be fair. So the best answer to do this is to deploy something like Tetration, which is a fantastic tool for doing application dependency mapping. And that'll give you all the answers you could possibly want. But the pragmatic approach is, if you want to migrate into ACI and you don't know what your application is, or applications that are currently running on the environment, is that we want to take the network as it currently is configured. And that really gives us two deployment options. network-centric and application-centric. And that's, to be fair and make this very clear, that there's no button, there's no switch, there's no mode per se in the fabric. It's simply ways of deploying a single application profile to the network and how much information you have about that application. So a lot of people will do in applications where they don't really call it an application, it's really a collection of the standard VLANs and IP addresses and EPGs. And we may have no contracts in place, or at least a contract with an open ACL, so to allow all between any EPG. And that allows us to migrate existing networks as is without any additional changes. And some people, they stop there because, well, frankly, ACI is really good at doing that. And it's still a better way of managing your network, even without changing the way you manage and operate your network. If you wanted to, and it's completely up to you, you can then go back and try and improve those existing migrated applications. You can go back and add filters more appropriately, maybe change the VRFs, maybe go back and add titration and learn how they actually operate. But what we find is a lot of people will just ring fence the existing networks and say, right, they're up and they've migrated, we're going to leave them alone, but we're going to deploy new services using application-centric mode. And that's fine. They obviously both work well together. We've got many customers who do this direction. Some even take it further through mergers and acquisitions and have multiple tenants for different customers running different legacy deployment models, and then have one new tenant for a combined entity that's running application-centric. Okay, so moving on, I'd like to go into the security a little bit more. Now, in a recent survey, we found that 76% of the security team's time was really taken up in the data center. And by that, we really mean that 47% was running on the servers and 29% was managing customer data. Now, 47% of your time managing security in the data center is a lot of your day-to-day operations. So we want to try and make that better. Now, we've kind of alluded to it with the way we do ACI, but just to reiterate, ACI works with a zero-trust default configuration. You can't just connect to the network and expect things to work. You can't connect two switch ports on the front of a leaf and expect to be able to communicate across the default LAN. Default VLAN doesn't work. Without a contract between EPGs, there is no communication. We do allow communication within the EPGs, which is why if we do a simple network-centric model, we tend to move a VLAN across. We're still maintaining all the communications between services inside that VLAN. But saying that, we can, with a flick of a button, turn it into an isolated endpoint group and restrict access between devices within the same endpoint group, much like a private VLAN does. We can go one step further and add filters to that and actually say exactly what TCP ports you can use between devices within the EPG. So contracts in ACI have an implicit sense of direction. There's a provider of a service and a consumer of a service. So in this example, EPG Green is providing TCP port 80 and TCP 443 to EPG Blue. Now, EPG Blue can then connect back into the provider on 80 and 443, but nothing else, as you expect from any ACL. So this is really a distributed firewall implemented on those top-of-rack switches. We also use these contracts to do service chaining. So within the same contract, we can add this layer 4, layer 7 service graph and say that between the provider and the consumer, you first have to go through this chain of services. So in this example, we've got an ASA and then an F5 load balancer. Now we don't go into detail here, but they don't actually have to be in line in a networking sense. We can use policy-based redirection to say that even though your consumer and your provider might be on the same VRF, we can still intercept that traffic and send it to a different VRF and a different device, and then send it back and re-inject it back in again as well. So there's no requirement that these have to be in line in a networking sense. Now, we've mentioned before that external EPGs we typically have to configure manually. An IP address of what is your WAN, what is your internet. It would be much better if we could in fact use some sort of common external service that might have better information for us and share that information into the APIC controller. And a good example of this is APIC. So APIC is, excuse me, so ICE. ICE allows us to share information between the campus network and the data center network. So for example, if you connect to a secure group, you're authenticated into that group, we can then share that group information into ACI and use that as part of our policy set. So it looks a bit like this. We have security groups defined in ICE, learned into ACI as external networks, or these external EPGs, and then the vice versa, we take the application EPG information and send that back to ICE as well. So let's move on to ACI Anywhere. Now ACI Anywhere, make this clear, the data center is not really centered anymore. And what we mean by that is that data is now available anywhere in your network. I mean, it started off in your enterprise DC, but I mean, obviously most customers now are moving at least some of their components, whether they want to or not, to the cloud. And obviously that cloud might have different visibility and different security, and obviously you need different skill set to operate it. You might also have still services out on your edge network that still also need the same security and visibility. And depending on your industry, you might need services running out right at the edge, outside of your branch offices, on cabinets on the side of the road. And you really still want to be able to manage those if you need to as well. So we want to take the data center to where the data is. So we want to be able to break the data center networking away from just the physical on-premise data centers. We call this approach ACI Anywhere. Now there's three approaches to ACI Anywhere. The first one is ACI multi-pod and multi-site, where we take one data center fabric and we can extend that to multiple data centers, whether it's locally, within the country, or even between countries. We can then extend your ACI fabric down to remote sites that might not justify having a ACI fabric, multi-pod fabric deployed there. And that's remote leaf and virtual ACI. And finally, we can also extend the ACI fabric now into the cloud itself. And that's Cloud ACI, and we'll talk about that shortly. So ACI multi-pod, as the name kind of implies, is really taking that same fabric in one data center and mirroring it in one or more. And what we're doing here is really extending the underlay between the two networks. And we're managing both of those networks through one single ACI cluster. So logically, there's pod 1, pod 2, but they belong to the same ACI cluster, and they're managed through that single interface. Now that allows some key benefits. Obviously, we can move any workload to any top-of-rack switch now in any of these pods or any of these data centers. So that's the same top-of-rack capabilities, same routing. And if we have like WAN access in both data centers, then we can use whatever local WAN access to come in and out of the fabric, but also fail over left to right, or east-west as the case may be, to get access to the WAN or to other services, firewalls, load balancers as well. Now this works really well with synchronous replication storage, so RPO0, things like Pure or stretched Hyperflex cluster. Now with a synchronous replication between these sites, we can run any VM at any site at any time. Now multi-site allows us to take that even further and allows us to take multiple ACI fabrics and join them together. This is more of a hierarchy rather than sitting the underlay. We've built a separate VXLAN overlay over the top. So we now move on to the smaller sites. So remote leaf is where we can take two physical ACI leaf switches and deploy them over the wide area network to a site. And we still get the same benefits, top of rack, layer 3 routing services, and ability to run any workload on remote leaf or in a multipod, but without having to put all the infrastructure in place. However, you can go smaller still. And what's smaller than 2 switches? No switches at all. So we can go down to running a purely software environment. And this uses the AVE, the ACI Virtual Edge virtual machine to provide data plane connectivity. The final part I'm going to spend a bit of time on is cloud. So as of ACI 4.1, we can now extend the ACI policy constructs into the AWS cloud. Other providers are coming shortly. Now this allows us to treat the cloud as just being another site within the ACI multi-site topology. And we push the same policies to both, but use the cloud APIC, or effectively a customized version of the APIC controller for that particular cloud, to translate ACI policies to whatever's native to that environment. So for AWS, a tenant becomes a VPC, EPGs become security groups, and contracts become security group rules. So we're not trying to add anything new to the public cloud providers. We're just trying to translate what native services are available and keep that consistent. So you don't need to know how it works. We can just push that config through for you. Now, some example use cases, I'll go through this pretty quickly. We can extend, obviously, services and just use that site as it was a public cloud, as if it was another multi-site in place, and have have those resources available for those tenants. We can do cloud bursting, where we set up new infrastructure there on a temporary basis and extend the same configuration to both sites. So, and then no additional changes to the policy is required. And when we don't need those resources anymore, we can just wind them back again. Or we can share services out of the public cloud and back into your own environment. Showing DNS there, but there are other sort of cloud-hosted services you might want to share back into your on-premise. So now moving on to making the most of ACI. Now we've talked about how we integrate ACI with other things like the public cloud and with ICE, and a little bit about how we do it with hypervisors. We also now do containers, and we talk about Kubernetes, OpenShift, Pivotal, and we'll be able to integrate APIC with those container managers and provide a consistent network policy for containers as well. We obviously talk to most firewall providers, and this is probably an important part, Palo Alto, Fortinet. This is an example showing firepower, but it kind of works for most providers, where the APIC controller and the firewall manager can talk to each other through an API layer and share information. So any information like the content of an EPG can be shared into that manager as a network object. Now this allows the security administrators to build policies based on these pre-built objects without having to know what the IP addresses of the servers actually are. And we can combine those together through a service graph where the network administrator connects the connectivity to the firewall, but the security administrator is the one who actually sets the policy. And they don't actually have to know about the IP addressing or VLANs. And vice versa, the network administrator doesn't know how the security policy works. I'll click through this pretty quickly, but what we wanted to show here was the ability to stretch a firewall cluster between two sites in a multi-pod environment. They're really the one at the bottom here. That allows for a truly active failover scenario where we can move a VM from one DC to another and still have the same stateful TCP sessions in place through the firewall chain. But in multi-site, it's a bit different. We really want to keep that fault isolation model going forward. So we don't want active-active firewall split. We really want to have separate active standby clusters deployed in each site. Now ACI has we call it App Center, the ability to run third-party applications within the cluster itself. Now these include things like Splunk, Infoblox for IP address management, ServiceNow, and these are all available at the website above. So if you have these already in your environment and you're introducing ACI, you can leverage these and obviously improve the utilization of both services. Now within Cisco services, we have some important things like ACI and App Dynamics. Now, I'm not going to have time to talk about App Dynamics, but it does allow for, if you've got App Dynamics, we can talk to ACI and improve troubleshooting times, be able to drill down out of App IQ. Now, we mentioned tetration before, and tetration was really there around building those application dependency mappings and the learning how to build EPGs and policies. And we can take that information and then import it back into the ACI fabric. But what if you don't have tetration? And that's quite a good question, because tetration is quite expensive. It's a big hardware thing. So instead, we have a new function called the Network Insights Resources application. Now, this is a new function that's just been released in the last month, probably the last few weeks, in fact. And that allows us to use streaming telemetry from the hardware, the Nexus 9Ks, and from the software, and to collect that on the APIC cluster itself through a new big data application. And we use that for doing things like, obviously, network operations, hotspot, congestion, microburst detection. We get a lot of capability that we didn't have before about how actual flows work in the network that we previously had to rely on tetration to provide. And that gives us things like an event dashboard and a flow level dashboard that's very time series orientated. So we can go back in time, see what happened at any moment in time in the network. We also have a companion application called the Network Insights Advisor. Now, Network Insights Advisor is constantly looking at how your network is configured, comparing it against scaled best practices available, published best practices and scale limits, as well as known bugs and PSP certs. And it can alert you if something in your network, your particular configuration, is being hit by one of these particular bugs. And then obviously provide you some way forward to remediate that situation. Now these will live as applications on the APEC cluster itself. Finally, Network Assurance Engine. Well, not quite. The Network Assurance Engine, which is the proactive assurance, as we said before. And that allows us to preemptively find problems in a network before we've even sent a packet across the wires. Probably one of the more interesting things we've introduced, or about to introduce, is our SD-WAN integration. Now, that allows us to set SLA information within the application profile itself, so jitter, latency, packet loss, and provide that information up to vManaged, so it can determine what the best path is across the WAN to get access into our fabric. And obviously also between devices in the fabric itself, we're going from one data center to another through the SD-WAN. Now, we don't automate everything through ACI. Obviously, we don't do anything at the software layer. So we want to make sure that you don't feel like you're constrained at all. And we have a very comprehensive API within the ACI fabric itself and SDKs for development that expose that logical abstracted tenant model, which is really the point where you want to make your changes to. And we can then use that with things like Ansible, Chef, or those third-party applications, vRealize, to automate your entire network end-to-end. So that's building their application and building the networking for that application at the same time. So where to go next? Well, the key thing we want to point out here is that intent-based networking doesn't start and stop in the data center. It is really only one component. We have intent-based networking for the access, which is DNA Center and the Catalyst 9Ks. And we have obviously intent-based networking in the WAN, which is our Viptela or Cisco Meraki. And what we want to show here is really the fact that while these have separate control planes, and we don't want to share a control plane between them, they're all optimized for a certain function, we want to be able to share information between them. The more information we share, the better they all get. So we've seen before the integration to SD-WAN, the integration to ICE for SDA. You know, the more we have, the better it works together, the easier it is to manage and operate your network. Now, ACI and, well, Cisco in general is really the leader of intent-based networking, according to Gartner. And we're really only getting better. Now, Gartner expects that most people will be automating the majority of their DC tasks by 2021. We want to make sure that we give you an option on how to get there. We want to say that this is our best approach. We want to help you get there. And if you like what you see, come talk to us. We're going to help you get there. So thank you very much for coming this morning. I know we're a little bit over time, but I wanted to see if there's any questions. I will be at the Meet the Expert stand later on today. Later on tomorrow afternoon. There are plenty of ACI things. If you saw the session this morning, there's plenty of ACI breakouts available, and also hands-on DevNet sessions, which I strongly recommend going to. So thank you very much for coming this morning. Please, if you have time, take the time to review the session. Let me know how you think. All right, thank you very much. Thank you.